Welcome to today's Summary Algebra and Geometry online seminar. We're in for a treat because we have Monica Vazirani from UC Davis talking today. Monica, let's see, she did her postdocs, if I remember correctly, all over the West Coast, Berkeley, Caltech, San Diego, and now you're a professor at UC Davis. Personally, Monica is a very special connection to me because when I was a first-year grad student, went to a summer course that you taught in Montreal. That's where I first learned about Hecke algebras, their representation theory, Cauchy-Linguistic polynomials, and your energy was totally infectious. And so that kind of was a hugely pivotal moment for me. So I'm very excited to have you here today. And so, yeah, let's get started. Take it away.
All right. Well, thank you so much for inviting me. And I love the time zone difference because it's like 5 p.m. for me here, which is great. I'm awake. All right, so my title is From Representations of the Rational Cherednik Algebra to Parabolic Hilbert Schemes via the Dunkl-Opdam subalgebra. And so the definitions of all these things, well, if they won't be stated really rigorously, they'll at least be sketched later on. But I think I knew there was a bunch of people that had to leave at that halfway mark. So I kind of reorganized things, and we'll see how it works out for I put all the combinatorics up front and some of the algebra and the details at the end. So everything I'm talking about is joint with Eugene Gorski and Jose Cimental. And you can find this on the archive. And also, they have given talks also on this work, and I put the links here, and I can also mail them to you if you wanted to see. I think Eugene focuses a little bit more on geometry than I do. And Jose focuses more, you can say some of this stuff more in terms of like Coulomb branches or affine Springer fibers, and if you want to hear more of that side of it. And they both give excellent, excellent talks, so totally worth watching if you don't have Zoom fatigue. All right, so, okay. So as I start many of my talks, let me start with the symmetric group and remind you, like, what do we do to study the representation theory of the symmetric group? Well, a lot of us, we like to start with the combinatorics, or, what are the combinatorics you see in the representation theory of the symmetric group? You see the combinatorics of Young diagrams, like pictured here in English notation, or sort of synonymous that are partitions. So the partition 3, 2 of 5, because 3 plus 2 is 5, or 3 boxes and 2 boxes. And so this combinatorial gadget goes hand in hand. You can't study the symmetric group without encountering partitions, and in particular, the irreducible representations of the symmetric group, say of S5, are indexed by all such pictures. It's very combinatorial. Also, the dimension of such a module is given by the number of standard Young tableaux. So the number of ways, since you have 5 boxes, you fill it with the numbers 1, 2, 3, 4, 5, so that entries increase across rows and down columns, and those are called standard Young tableau, and I'll abbreviate SYT. Okay, and today we're going to study representation theory. We're going to see some Young diagrams appearing and some ways of filling them that is going to correspond to bases. All right, and there's lots and lots of beautiful combinatorics that goes into that. You can also study the representation theory from a more algebraic point of view. So for instance, if you go to the group algebra of the symmetric group, there's a nice commutative subalgebra sitting inside there, generated by the Jusis-Murphy elements. And one thing that's really nice about it is that commutative algebras, as you know, they're simple modules or one-dimensional, at least if you're over a big enough field. And so you can find basically a weight basis or simultaneous eigenbasis for these operators that you can simultaneously diagonalize. Turns out that your weight spaces all have dimension 1. Like, in Lie theory, that doesn't have to happen, but it does here. And so you basically get this commutative algebra. Commutative subalgebra gives you a really nice basis. And then if you look at those eigenvalues or those weights, the combinatorics of those weights rediscover the combinatorics of these standard Young tableaux. Okay, so that's a nice algebraic way to access this information. Another way you could study the representation theory of the symmetric group is through geometry. Okay, I confess I never study it that way. I'm not that geometric. that you can construct the representations of the symmetric group by looking at, homology or cohomology, whatever your favorite is, of, some nice geometric space. And you can use Springer theory for that. And, a favorite geometric space you might take is a space of flags. You might have a bunch of nested vector spaces, each of codimension 1 in the next, okay? And then, your job is to get elements in the symmetric group to act on, well, they don't have to act on the flags themselves. It's on the homology of the space where they're acting. And that's a nice geometric construction. And there's, again, lots of beautiful geometry in there, which I'm not an expert in, despite the decades I've had to become an expert. All right, so what I'm going to talk about today is a geometric construction of a representation of not the symmetric group, but a much bigger algebra called the rational Cherednik algebra. But it's the one that goes hand in hand with symmetric groups. I'm only doing this in type A, okay? And my geometric construction is not of all representations of this big algebra. That's some kind of big generalization of the symmetric group. It's only of the so-called trivial representation. And furthermore, there's this rational Treadmic algebra has these two parameters, t and c. We can normalize the presentation so that we can, if t is not 0, we can assume it's 1. So if we're at t equals 1, our parameter c has the form m over n, where the n is the same n as in the Sn, and they're relatively prime. We also have results for the t equals 0 case, but I'm not going to talk about that today. Okay. All right. So, yes. Okay. So to give this geometric construction, I'm going to have to define this geometric space. That's kind of like a space of flags. Okay. I'm going to have to tell you what this big algebra is as well, and the way, but I'm really going to start with the combinatorics of the representation. In other words, for the symmetric group, I said my representations had a basis indexed by tableau, and I'm really going to start with looking at tableau and then build it back up to the more general theory and hope that that level of organization works. If not, the next time I give this talk, I will reorganize everything. All right, so here's the theorem that we're heading towards. So if we take this rational Cherednik algebra that we attach to the symmetric group, our parameter t is 1 and our other parameter has the form m over n for m and n coprime. So that algebra acts on the homology of some geometric space. So it turns out it's not just the homology, it's the localized C star equivariant homology of the parabolic Hilbert scheme of a plane curve singularity C. So these parameters m and n that are coprime, I can make a curve cut out by the equation x to the m is y to the n. And again, this n is the same n as in the symmetric group. So I can make this curve. I can define the Hilbert scheme on it. I can define this parabolic Hilbert scheme, which is some big piece of them, like lots of pieces all glued together. All right. And then this algebra, the RCA, the rational Treadmic algebra, acts on its equivariant homology. And when I look at what is the structure of it, I recover this so-called trivial module. Okay. All right. As a corollary to this, the symmetric group has a trivial idempotent, E, and so you can sandwich your algebra in between this idempotent, get this corner ring, and then you can also hit the representation with this idempotent, and then you're going to get the C star equivariant homology of just the regular old Hilbert scheme without the word parabolic in there, and that's a well-known result. Okay, so we can obtain that as a corollary to this. For related work, instead of having the rational Treadmic algebra, which I haven't defined, there's something called the trigonometric Treadmic algebra. So if you want to see a geometric construction of the representation of that algebra, very similar work, you can look at earlier work of Oblomkov and Yoon. Okay. Or you can work again for getting these geometric actions, work of Listed, Varignolo, Vasaro. That's more in the language, instead of Hilbert schemes, looking at affine Springer fibers. And if you look at Webster or Garner Kivinen, they look at generalized affine Springer fibers, and again, having these nice geometric actions of these algebras and more general algebras acting in these spaces as well. Okay. So even though I still haven't defined what the rational Treadmic algebra is, let me just stick with the theme that it's kind of some souped up version of the symmetric group and tell you something about the structure of its representation theory. So it has a highest weight category, category O. O sub C, there's this parameter C that floats around, of representations. And we know what the simples look like, okay? We call them, L sub C of mu, and mu's are partitions of n. So in that sense, you're like, oh, it's not that different from the symmetric group, because simples of the symmetric group are parameterized by partitions of n. Okay, so how terrible can it be? And we know how to get the simple. We can realize the simple as a unique simple quotient of some standard module that we know how to build. And how do we build that up? Well, we have the symmetric group. We enlarge it. There's some larger subalgebra that sits inside the rational Cherednik algebra. And you just basically take this representation you know and love of the symmetric group, you extend the action and you induce it up. And there you go, that's at standard. So even though I haven't told you what these are, the standard module is completely understandable and controllable because we know how the symmetric group acts on it. And then once you understand the definition of this algebra, it's just an induced module. So completely explicit, but how is this simple quotient cut out? That can be more complicated. But we understand, we understand how to parameterize them. We understand a lot about them. A nice theorem, you might say, well, so this simple L is a unique simple quotient of the standard delta, but maybe they're the same. And a lot of the time they are the same. If this parameter C is not rational, or if I write as a rational number, if it has denominator greater than n, then we know that this standard is going to be simple. In other words, we understand those simples. Those simples are really easy to understand because they're just these standard induced modules. Now, in the case where C is m over n, for m and n relatively prime, and that's where the geometry is living, and that's where the results are living today, then, well, actually a lot of the times you're lucky and your standard module is simple. But when it's not going to be simple if mu is a hook. So what is a hook? It's a partition that looks like so. Okay, so some number and then a whole bunch of ones that add up to n. Furthermore, in the case when we have all of these standards on hook shape that are not necessarily simple, we have a nice exact sequence. Okay, and I guess I should say, right, this is this resolves, this gives a resolution, whoops, of our simple module, and this is the one that we have the geometric construction of. Okay. So that was, oops, I think Beres, Eddinghoff, Ginsburg, I think I quoted them, or sorry, Beres, Eddinghoff, Ginsburg, as well as Ginsburg, Gouet, Opdam, Rouquier. Okay, these theorems go back to that. And so another thing that, if I have time, some of the machinery that went into understanding this geometric construction and some of the combinatorics that went into understanding this module gave a sort of elementary construction of this BGG resolution. You can really explicitly construct the maps there and understand them. And that was kind of satisfying because if you look at other existing proofs, they use more fancy machinery, like the KZ functor, that relates the representation theory of the rational Treadmic algebra to a finite Hecke algebra at parameter acute of, a root of unity. Okay, depending on that parameter C. Okay. All right, and so both things I'm going to talk about today, this sort of geometric construction or this other way of constructing these BGG maps, they make use of a different presentation of the rational Cherednik algebra than it might be the first one you've learned or the one you haven't even learned yet today. And they also make use of a corresponding nice combinatorial basis that you get out of the standard modules. All right, so let's jump into the combinatorics, even though we haven't defined the algebra that we're working with yet. So I claim these standard modules, they have basis indexed by the following data. So you let T be a standard Young tableau of shape mu, because I have the standard for mu, and a vector of length n consisting of non-negative integers. Okay. So that's nice. Again, remember this was an induced module, so we had complete control over it. So it makes sense that our basis is is indexed by something really controllable, along with what a basis of a representation indexed by mu of Sn should be. So in particular, in the case when mu is the trivial representation, there's only one standard tableau on the trivial. You have to fill with the numbers 1, 2, 3, n increasing. So there's only one t. So in this basis, you don't need to worry about t. The basis is in correspondence with just vectors of non-negative integers with n components. Okay, the basis of your standard module. So, all right. That's for general C, but again, the geometry and the BGG resolution was all living in the case when my parameter C is of the form m over n with m and n relatively prime. So theorem due to Griffith, if you look at this unique simple quotient of my standard, so my standard again, this is going to fit, right? So the standard had basis corresponding to just these vectors of the n. The standard has a unique simple quotient, L of Triv. And so how much is being cut out? Well, a basis of this is indexed by not all of these non-negative integer vectors. They're the ones such that the difference between any two entries is less than or equal to n. Okay, and if you hit exactly m, if ai minus aj is exactly m, then I has to be less than j. Okay, and I'm going to call this set capital A m over n. So let's see some examples. Let's say m is 4 and n is 3. So that means I have a size 3 vector. So if I take something like 4, 0, 0, that's good. Because I achieve the value 4 minus 0 is equal to 4, but 4 comes before the zeros. So that one's good. But if I take 0, 4, 0, that one's bad because this 0 is before that 4. And so I'm violating this condition here. Okay. On the other hand, something like 5, 7, 3, that's good too, because the differences between 5 and 7 are 2, and 5 and 3 are 2, and the difference between 7 and 3 is 4, but 7 comes before the 3. So that one's good as well. And I should say, some of you might be expecting that this should be finite dimensional. It's not. It's infinite dimensional, but part of that is the particular kind of rational Treadmic algebra of type A that I took. It's sort of more like the GL versus SL1, or rather, it's like I'm looking at sort of the permutation representation of the symmetric group going into the data as opposed to the n-1 dimensional standard irreducible representation of it. So this is kind of, it's like finite dimensional at heart, and then with like these kind of infinite dimensional fibers. So let's go with it. Okay, just in case this set being infinite was confusing you. Okay. All right. So I said that there was, okay, so here's the combinatorics. I have this irreducible module, and I've told you what index is a basis. But if you know this and love the symmetric group, you want a basis of tableau. So where are the tableaux in this? Okay, so here in the tableau, again, we'll keep n equals 3 and n equals 4. And let me just, right? So let's say my integer vector is 0, 0, 0. Well then, my tableau is just 1, 2, 3. what happens if I just take some other, some other integer vectors? I am going to produce tableau, and my tableau, well, they're going to be, row increasing, and they're going to have the property that I have exactly one residue mod 3. Right? They're distinct mod 3 and increasing. And I claim that my basis for my standard is going to be all such tableau. Okay, so I have 3 increasing numbers that are positive and distinct mod 3, and that those are in bijection with these 3 tuples. Okay, and how are they in bijection? Well, let's focus on, say, this example, 4, 0, 0. So I write 4, 0, 0. My standard tableau goes 1, 2, 3, so I have 1, 2, 3. And I want integers that are distinct mod 3. So let me scale the 4 and 0, 0 by 3 and 3 and 3. In other words, I'm going to take 12 plus 1 and get 13, 0 plus 2 and get 2, 0 plus 3 and get 3. So, but in this way, give me any vector of non-negative entries, add them to 1, 2, 3 after I've inflated them all by 3, and that's going to give me 3 numbers that are distinct mod 3. They're not increasing, so sort them so they are increasing. So 13, 2, 3 becomes 2, 3, 13, and then just stick them in a tableau, and there you go. Right, so the upshot of this is the standard modules have bases given by tableau, as you would want to expect. But it's not the symmetric group, so this gives you in some sense a feeling for how much bigger is the rational Treadmic algebra than the symmetric group, which is in the symmetric group we're only allowed to fill with 1, 2, 3. With the rational Treadmic algebra we're able to fill with all positive integers, but we have to have them distinct mod 3. All right, and now you might recognize this process of scaling these entries by 3 and adding them to 1, 2, 3. That's a translation in the affine symmetric group by this vector. And so you could say I sort these guys to get the tableau 2, 6, 7, or you could say translation by this vector is a well-defined affine permutation, and the minimal length coset representative of it is my tableau. So for people who understand those words, that's another way of saying what's going on. And let me, yeah, so I also said algebraically I'm going to use some commutative subalgebra and look at how that's acting on my basis and that I can have a weight basis. And how do I get from tableau to weights? I basically am going to label my diagonals of my tableau, and I'm just going to look for which diagonals are 1 and 2 and 3 on, and that is going to give me something about the U weights, and I'll have to fill in more details about that as we get more into the weeds of things. But there's a way from each of these tableaux, or from each of these integer vectors, to read off a weight that's going to correspond to some big commutative subalgebra acting. But we're not ready to get into the details yet. All right. So let's see, do I want to say this yet? Yeah, just as a preview of what's to come. So the simples were indexed by these integer vectors that had this condition about the differences being bounded by m, and if the difference is exactly m, you had to have the 4 coming for the 0. So like this guy was not in my set. This guy corresponds to a weight vector that's not going to be captured in my irreducible quotient. It's going to be captured in some proper sub. And just to give a preview of what the combinatorics is there, is that if you take 1, 3, 14 and you add m times n, which is 12, to everything in sight, you'll get 13, 15, 26. And you might think that I want to take that 13, 15, and 26 and just slide it over and stick it next to here. Well, that's bad because you're not increasing. But you could shift it up 1 and put the 13, 15, 26 up there. And when you do that and you keep repeating, you realize that you can change your fundamental domain to look like a shape like so, which is a hook that's a little taller than the hook we had before. So I'll go into detail of this more if there's time, but that's just a preview of why it's nice to have a tableau model. When you have this tableau model of this basis, you can see very nicely why this set is cutting out the simple. That this set that's cutting out the simple is basically cutting out set of fillings such that they have a nice structure when you try to make them sort of periodic. All right. So, right, yeah. So in other words, so this set, AMN, it basically detects whether the tableau that we create from the vector A, that if we take this first entry and add MN to it, is it greater than the last entry? That's basically what the set AMN does. And so it's the set that makes a nice, pretty combinatorial picture of the basis. All right. So yeah, let me skip that. All right, let's go into the geometry. So I'm going to take this plane curve singularity. I'm going to take the set of points cut out in the complex plane by x to the m is y to the n. The n is the same n as in my symmetric group, and m and n are relatively prime. Okay. Now, I want to look at its local ring of functions. So I want to go to not just polynomials, but power series. So you join xy mod the relation x to the m minus y to the n. If you want, you can think of that as power series you can think of x as being z to the n for some other variable z, and y being z to the n. So you can think of generated by z to the n and z to the m. Okay. And because y to the n is x to the m, if we want to make a basis of this, we can have any powers of x's, but the powers on y, we can just go from 0 to n. All right, so that's my curve. Now, what's the Hilbert scheme of k points on C? And again, I am doing this sort of local thing, so I'm being sort of special about 0. So I want to take ideals in this local ring such that the codimension is k, and that's my sort of Hilbert scheme of k points on C. And I'm going to denote an ideal of codimension k by putting a subscript k on there. That's my Hilbert scheme. What's my parabolic Hilbert scheme? Okay. So let me build it up in 2 steps. So my parabolic Hilbert scheme, indexed by a pair of integers k and n plus k, is going to be the following flag of ideals. So I'm in my ring. I take an ideal of codimension k containing an ideal of codimension k plus 1, da 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 da, all the way down to k plus n. And these are this k and n plus k. Oops, k plus n, n plus k, same thing. But I'm asking that this last ideal of codimension k plus b actually be x times my first ideal. All right. And notice that ik mod xik, that will have codimension n because I have my relation, my x to the m is y to the n. Okay. And now, if I say my parabolic Hilbert scheme of C and I put an x up here, that's the union over all k of these guys, right? So I have my ring, I start at some fixed codimension, and then I go down one at a time, and then I have this kind of periodic behavior, and I want to take the union over all k of these. So that is my big geometric space that I'm going to take equivariant homology of that, and I'm going to get my trivial module, which has this basis indexed by these special integer vectors. I'm going to convince you, at least at the moment that it's a vector space, those end up being the same thing. All right, equivariant, how can I be C star equivariant? What's a C star action? Well, that's easy, right? You can just scale x and y by, well, you have to scale x by, say, alpha to the n and y by alpha to the m because you're on your curve where x to the m is y to the n. Now, because m and n are relatively prime, the fixed points of this action are going to be flags of monomial ideals. Okay, and that means that when we go to the homology, a basis of homology corresponds to just flags of monomial ideals. So combinatorics just got really nice and really easy out of this complicated Hilbert schema, and this is also part of why it's nice to take things local. So you can just deal with monomial ideals. All right, so let's look at monomial ideals. Okay, so remember that so a monomial ideal is one that's generated by monomials. And of course, if I contains a monomial like x to the a, y to the b, it's going to contain also x to the a plus 1, y to the b, and x to the a, y to the b plus 1. And there's a really nice way of drawing monomial ideals. So for instance, if we take the ideal containing, so let's see, so x cubed and xy squared and y to the fourth, well, because you're closed under multiplication by x and multiplication by y, you're going to contain all of those monomials. You'll contain all of those monomials. You contain all of those monomials. And so the monomials that you basically don't contain all fit in this nice Young diagram, basically. Okay, and so a nice way to draw monomial ideals is just by taking some nice Young diagram that's justified. Now I'm in the French way, that my gravity is going down there and over there. If I had my druthers, I would have had the y's going in the other direction. It would still look like an English Young diagram. But most people don't do that in geometry, and Eugene and Jose would not have put up with that. Okay, so that's a monomial ideal in general, but remember we're on this curve, right, where x to the m is y to the n. So let's look at, say, where, again, we're always taking m is 4 and n equals 3 for these examples. So, you know, let's say that, sorry, I should have said, excuse me, right? So the stuff in the monomials in the ideal are out here. And so so these monomials are basically not in the ideal, and they form a basis, basically, that, you know, plus the ideal. So this guy would have codimension 1, 2, 3, 4, 5, 6, 7, 8. So how many boxes under the diagram gives you the codimension? Okay, so let's say we took, right, an ideal corresponding to all the monomials outside of here. Because, remember, so y cubed is x to the fourth, or no, yeah, y cubed is x to the fourth here. So I don't need to draw y cubed. I can just cut my diagram here, and I can keep control of higher power of y's by telling me what's going on with x's. Also, suppose my ideal contains x cubed y squared. Well, then because it's closed by multiplication by y, it would contain x cubed y cubed if we bothered to put in a y cubed row. But x cubed y cubed is the same as x cubed x to the fourth, because we're on the curve where y cubed is x to the fourth, and that's x to the 7. So because I contain x cubed y squared, I'm forced to contain x to the 7. That means that even though for an arbitrary monomial ideal, I can have any old diagram, this tells me that anytime I have a step here, I have to have a step that's no more than 4 away from that step. Okay, so that means this width of this, I mean, this can be as long as it wants, but from the start to the finish, they can't be more than 4 away. And this condition should be reminding you we had this set A m over n that had some condition about the differences between the entries being less or equal to m. That is, we're sort of seeing that happening here with these ideals. Okay. So, let's see. We're at the 40 mark, but we started a few minutes late, so I'm gonna go a couple minutes before the 40-minute break, if that's okay. All right, so this is, yeah, so the pictures of my ideals in this space are these staircase pictures, but the height is only as tall as n because of this relation. And the width of the bounding box is less than or equal to m. Okay, so those describe all my monomial ideals. And, right. So now I want to take a flag of ideals, okay? Because my parabolic Hilbert scheme is built from flags of ideals, but it's a flag of ideals such that, so we'll have a bunch of ideals, so that'll be like a sequence of these staircase pictures, but the last guy in the staircase is supposed to be x times the first guy in the staircase. And so what happens if you're multiplying every monomial, generating it by an x, that just moves these vertical steps each over 1 to the right. In other words, I have a new bounding box that's moved everything over 1 to the right. And so another way of thinking of it is I have to add in, or rather, if my containment's going that way, I'm really subtracting, sorry. I am subtracting these 3 monomials sort of out of the ideal if my containment's going that way. Or if you think of the containment going this way, right, you're getting 3 new monomials that you're adding in as you build up. 1 from each row. And that's because of having this x condition here. Okay? And so a flag is just then some way of deciding which of these boxes comes first, second, third. Right? And so you might think there should always be n factorial ways of doing it, but that's not true for 2 reasons. So one is, if I had a tall vertical step, right, I can't sort of get this monomial before that monomial, because if you put in that monomial first, you would get something that doesn't look like a Young diagram. You wouldn't be close under your multiplication. It has to look like a Young diagram. But we also have this bounding box of the partition being less than or equal to m. And if you, for instance, if this is just tight at m, and I add in this monomial first, suddenly my bounding box is too big. It's too wide. All right? So not every way of deciding how to add in a box in each row will lead to an actual flag of ideals. And so let's just see, right, so for instance, if let me take a tuple of vectors, say 3, 7, 5, and tell me how does that get me a flag. So 3 and 7 and 5 will basically say at the x cubed, x to the 5th, and x to the 7th, I had better have vertical steps, and well, it has to go like so because the 3 and the 5 and the 7 cascade down, so that tells you where the powers of y go. And then the fact that it's 3, 7, 5 will tell me first do it at the vertical run being 3, first do it at the x cubed, then do it at the x 7th, and then do it at the x to the 5th. So that's this 1, 2, 3. All right, and so again, first I am here, I add in that monomial, I am here, then I add in this monomial, and then I'm here and I add in all 3. Or maybe I meant subtract all 3, because again, your ideals are getting smaller and smaller. Okay. And the fact, again, so the fact that at each step, the flag still needs to have width less than or equal to m, that gives this condition that if I call this vector c, that, you know, the ci's minus cj's all have to be less than or equal to m, and if they're exactly equal to m, then I has to be greater than j. And if you were paying attention, that's the reverse inequality that we have with the a's. So because of the combinatorial conventions we had of the codimensions going like this, but then it means the containments go like that, this c vector that describes my flag is kind of upside down from my a vector condition that we had from the Trigonometric algebra. So let's just do this one example, then good place for a break. So in our set capital A m over n, 3 over 4, it was 4, 0, 0 that was bad. So that means in the geometric world, it's actually 0, 0, 4 that's bad. And let's see why 0, 0, 4 is bad. So 0, 0, 4 means my monomials that I'm adding have exponents on the x, 0 and 0 and 4. And because it's a Young diagram, the zeros have to be there and the fours have to be there. And so this is my first ideal. The fact that it goes 0, 0, 4 means I am making my flag by saying 1, 2, and 3. So the 0, 0, 4, and you can't go 0, 0, 4. Okay. And so, here's my flag. First, I put in that monomial, then I put in that monomial, and finally I put in that monomial, and at the end, it is x times what I started with. If you try to do that with 0, 4, 0, so that means the 0 is at the first and third entry, so I have a 1 and a 3 there, and the 4 is at the second entry. Okay, so first I would add in that monomial, everything's fine. But second, I would add in for that monomial, and now I've broken my staircase rule that this width should be at most m. And if you check, the ideal you'd want to cut out by this staircase is the same as one cut out by a narrow staircase. In other words, it's not really a flag. My codimension didn't jump. Something went wrong. This isn't a valid thing that we do. Okay. All right, and I will pause there for a little break.
All right, great, thank you. Are there any questions before we pause for break?
I've got one. I'm confused that the standard modules indexed by non-hooks are irreducible. I would have thought that was not.
Oh, no, they're not. They're not irreducible.
Okay,
you have
great.
The standards. Okay. There's these maps between the different standards. Oh, it's by non-hooks. By non-hooks. Yeah. The ones indexed by non-hooks are irreducible, and they're basically in their own block. Is what happens.
Okay.
Yeah.
Mm-hmm. Yeah.
Right.
All
Yeah.
right.
So if they're an induced module, if they were a proper sub, then some other induced module should surject to that sub, and that would mean you'd have something that would have basically, sort of like the same central character, not this in the same block, and there's just nothing else. If it's not a hook, they're all in their own different block. At this parameter c is m over n.
You've set up really nicely all these points of inside this Hilbert scheme, parabolic Hilbert scheme. Can you produce a bijection to the points of the corresponding affine Springer fiber?
Oh, I'm gonna say yes. Now, if you ask me to explicitly do that in real time, I totally wouldn't be able to.
Well, you don't have to do it real time, but is it so you've got this wonderful lattice of ideals, or I shouldn't call it lattice, it's chain of ideals with a condition. And of course, on the side of the affine Springer fiber, if I'm working inside the loop Grassmannian, again, I have chains of subspaces with a periodicity condition. So is it mirrored in that nice way?
I'm going to say yes. And I think even in the paper with like Jose and Eugene, we even talk about that point of view,
Okay.
Especially when we're talking about how it's related to the work of Gardner and Kivinen. But I am fuzzy on the details of explaining if it works exactly like you think it should.
Okay.
Of I think it works better with a generalized affine Springer fiber. Like you have this the matrix the matrix that you're saying should preserve the fiber that you want.
Yeah, what does generalized mean? I mean, the matrix that I usually use for M over N is essentially a cycle in the symmetric group, except multiplied by itself M times. And then it's got epsilons somewhere, or it's got the parameters, the loop parameter somewhere. So that's the matrix that I would want to use, but I don't know what
that's what you want to use here. But I think that generalized, I think, allows other kinds of matrices.
Great.
Thanks, Monica.
Okay.
All right, well, let's get back to it. Monica is going to give us part 2 of our wonderful talk.
All right, part 2. So, so part 1 what this last bit was supposed to convince you of is that we have a geometric space, right? That we have some geometric space that has to do with these, these flags of ideals, and that they're in bijection with and that these give you a basis of the homology of the space, and that's in bijection with what we said parameterized another basis. So at least as vector spaces, it should be believable that this is a geometric construction of that trivial module. Okay. So let's see. And again, the tuple, the n tuple that labels the flag of ideals is in reverse from the n tuple that labels this, periodic tableau, but that's, easily rectified. Okay, right. Yes. So this outlines a vector space isomorphism from, this basis is in correspondence with flags of monomial ideals, which are given by these tuples C that satisfy this condition that the differences between the C's are bounded by M, and if it's exactly M, the plus M has to come later. Versus our trivial module, we said, was indexed by these tuples A, where again, the differences between the coordinates was bounded by M, and if it's exactly M, the higher one had to come first. Okay. All right, so that was to pre-break, to just give the combinatorics and try to convince you it was matching up. Now we have to give some of the hairier details. For instance, what is the rational Cherednik algebra? And what is the commutative subalgebra that's going to give us our nice bases and line up our data? And if time, what's going on with actually explicitly giving these BGG maps? All right, so the rational Cherednik algebra, for the purposes of this talk, I'm taking the group algebra of the symmetric group, and I'm throwing in two polynomial subalgebras, okay, so as a vector space. And there are relations, which I'll get to in a second, but before we get to the relations, let's revisit our standard module. So our standard module, even before I had assigned RCA, I said you take the symmetric group part and one of your polynomial subalgebras, the y's, and you take the irreducible representation for the symmetric group indexed by mu. This polynomial subalgebra of the y's, you just say let them act as 0, and so now that gives you a representation of this bigger algebra. Oh, sorry, and the semi-direct product here, so one of the relations is the way that the symmetric group interacts with the y's, it just permutes the variables around. Okay, and so you induce that guy up. And then because this is true on the level of a vector space, that means a vector space basis of my standard module is given by, well, what's left over when you get rid of the symmetric group in the y's is just the polynomial in the x's. So as a vector space, the standard module is just the same as, say, polynomials in the x's tensor with your vector space indexed by mu, which has, its basis has to do with standard Young tableau of shape mu. Okay. And now you should believe the statement that what index a basis of my standard module? Well, a basis of polynomials tensor a basis of my mu. So mu has basis standard Young tableau. Polynomials has basis monomials. And monomials are indexed by what are the exponents, and that gives me my n vector here. Okay. So in particular, when we take the standard for the trivial module, this guy's one-dimensional. So as a vector space, my standard trivial module just looks like polynomials and x's, which has basis monomials, which are exactly corresponding to non-negative integer vectors that just tell me the exponents. So a1 through an, x1 to the a1, x2 to the a2, and so on. Okay. So that's filling in some things from before. All right, but what are the relations between the x's and the y's and the permutations? Well, I said the x's are a polynomial subalgebra, so you can just say the commutator of x's is 0. The y's are a polynomial subalgebra, so the y's commute with each other. How do y's and x's interact? If you want to take, the commutator of a y and an x, if the subscripts are different, you get c, which is my parameter, times ik denotes the transposition in the symmetric group, swapping I and k. All right? And if I take the subscripts to be the same, you get t times your identity, so that's my other parameter, minus c, that's my parameter, and now it's the sum of a whole bunch of transpositions. And so your I is fixed, so you just sum over all transpositions that involve an I. Okay. And how does the symmetric group interact with the x's and the y's? It just permutes around the variables when it moves past them. It's like a semi-direct product. All right. Now, as long as a was maybe not a great letter, as long as a is not 0, if I scale t and c by the same a, and you think about all these relations and what's happening, you get an isomorphic algebra. And so you might as well scale away the t and let t be 1, and then we write hc for h, 1c. Unless t is 0. If t is 0, you get some totally different creature, h0c, and then you can scale away the c to be 1. And again, I'm not going to talk about that in this talk, but in the paper, we do talk about that a little bit. So versus h, say 0, 1, which is a very different creature. Okay. All right. Now, that's the usual presentation that people kind of know and love of the rational Treadmic algebra. But let's use a slightly different presentation that's going to help us see the connections between the combinatorics and the geometry. So I'm going to let tau be the element in here that's x1, and then multiply it by an n cycle. And I'm going to let lambda be take y1 and multiply it on the other side by the inverse of that n cycle. Okay? And for later use, tau is going to correspond to some geometric operator capital T for when it acts on this parabolic Hilbert scheme. And lambda is going to correspond to some geometric operator capital lambda. All right, so just out of laziness, just cutting and pasting, and actually probably these numbers are no longer valid. What are the relations between, excuse me. So another way that you can generate the rational Treadmic algebra, you can just take tau, just take lambda, and then just take the SIs, in other words, the symmetric group. So that's enough to generate, right? So similarly, you could have taken the symmetric group stuff. Because of the way that the symmetric group permutes the variables around, you could have just taken x1 and y1 in the symmetric group. Well, if you've got x1 and y1, you can get your tau and lambda, but if you have tau and lambda, because you have your whole symmetric group, you can recover x1, you can recover y1. So very believable that these are other generators. Okay, and then they satisfy a whole bunch of relations. Okay, but the relations that I want to sort of focus on is that when a tau moves past an SI, it changes it by, let's say right to left, it decreases the index. Whereas when a lambda moves past an SI from say right to left, it increases the index. So tau and lambda are kind of like your diagram automorphisms that want to shift up like an S1 to an S2 or an S2 back down to an S1, but not exactly because they're not invertible, right? So let's go back here, right? So these two guys are not invertible. So shifting forwards, you think should have an inverse shifting backwards, but not exactly, right? The product of these guys, it's like X times Y. But combinatorially, they sort of behave like that. Okay. And indeed, we're not in the affine symmetric group. You don't actually have an S0. So sort of if you did have an S0, you could imagine that your lambda would push you down to an S0, and then you push down again, and you'd end up at n-1. And so that kind of morally happens, but it's not really there. And let's see, ignore for the moment these other generators used in here. Okay, so that's an alternate presentation. So in other words, if and the ones that I highlighted are things that just involve SIs and taus and lambdas. Okay, so I claim that these highlighted relations are enough to give a different presentation of the rational Cherednik algebra. And so why do that? Well, if I then have a geometric space I want to act on, and I have these operators of the symmetric group acting, that means that I just have to show that I satisfy these highlighted relations, and then I will have a module for the rational Treadmic algebra. Okay. Now, what's going on with these UIs that are also appearing in these relations? Well, those are wonderful, wonderful, wonderful elements. There are these Dunkl-Opdam elements or Dunkl-Opdam operators, and you can define them by UI is xi, yi minus c, that's my parameter, times the following sum of transpositions. Okay. It's a fact, it's a theorem by Dunkl-Opdam, that these guys all commute with each other. So that gives me some nice large commutative subalgebra. And you might say, why would I do that? I mean, I was talking about how it's great to have commutative subalgebras, and you could say, here's a commutative subalgebra. So why don't I look at how this one acts? Well, the standards that we looked at, remember we inflated them up to saying the y should all act as 0, and then we induced. So the y's are going to act nilpotently, always on my standard modules, and therefore on these simples that live in this category. And so if I try to find like a weight basis using just y's, I'm out of luck because they act nilpotently on everything. Similarly, the x's are acting, well, they're acting freely. Yeah, they're acting freely on the induced guys. So, you know, having this commutative subalgebra acting, it's sort of, things are growing too wildly. And the u's just kind of split the difference. And it turns out that the u's have a nice spectrum acting on, at least a good parameters of C, acting on my standard modules. Okay. And so for those of you who know your Juices-Murphy operators, the UIs are just like the Juices-Murphy elements. Okay. And notice that U1 is actually, you can also write it as tau times lambda. So it's kind of like a push-pull. All right.
Monica, do they generate a maximal commutative subalgebra?
For generic C, it should be. I think and if you're in characteristic 0, I don't want to say for sure it can't get any larger if you have some funky C. I think there's some work of Brundon that probably says exactly whether it's true or not. I don't know, Arun, if you...
But from the Coulomb branch perspective, we always get this maximal commutative subalgebra, like this integrable system appearing. I wonder if this is exactly what you're just writing down combinatorially.
At least when things are generic enough, for sure. The only thing I'm not sure of is if you're in some weird special something, if you could get more things commuting, like you know, like the t equals 0 land. There's more stuff that enters in and commutes. So so that's why I don't want to say it with absolute confidence. But I think in the realm that we're living in, for C is M over N, my guess is yes, but I don't want to commit to that. Great question. Right, okay, yes. So if you just take the symmetric group and U1 or all of the U's, they form a degenerate affine Hecke algebra. And so you can just look at the relations between simple transpositions and the U's. You know, they mostly commute ones that are nearby. There's a cost in this parameter C. And so now, you know, you can look back at the relations and see, now that we have the U's, you know, taus interact with the U's also by kicking up the subscripts, whereas lambdas interact with the U's by kicking down the subscripts. So again, it's kind of see, now that we have monomorphism, my favorite relation is that, or one of them. So what happens when you wrap around? You know, you'd want to kick, you know, you'd want to go from UN to UN plus 1, but you get, you know, U1 minus T. So that says that what I like to do is to actually think of the u's as not just having u1 up through un, have ui for all I and z, and just set, you know, every time you go up a sheet by n, you subtract off some amount of t. And that's my favorite way of acting. And then you can have the symmetric group acting sort of periodic by functions, and you can think about really just moving around the subscripts. So if you conjugate a UK by an SI, you'll get, you know, u sub SIK, either plus nothing or plus or minus CSI. And so let's look at projecting this degenerate affine Hecke algebra. There's a vector space, looks like symmetric group and polynomials in the U's, and just project the symmetric group by sending a sigma to a sigma, and let's send U1 to 0. And let's figure out what happens to all the other U's. So using this formula, right, U2 is equal to S1 U1 S1 minus CS1. Again, this parameter C shows up. And to make this be a homomorphism, that means we're going to send it to U1, which is 0, minus CS1. So writing S1 as a transposition 1, 2, we get minus C1, 2. Likewise, U3 is S2, U2, S2 minus CS2. And that means we're going to take what we got from U2 and conjugate it by 2, 3, and then subtract off C2, 3. And in total, you get minus C1, 3 plus 2, 3. Right, for U4, you do the same thing. You're conjugating this guy by 3, 4, and then subtracting off the C3, 4, and you get minus C times the sum, 1, 4 plus 2, 4 plus 3, 4. And you see that you indeed, for those of you who recognize it, this is what I would call the fourth Jusis-Murphy operator. It's a sum of all transpositions I4, where I is less than 4. Okay? And it's well known that these guys commute with each other, that these guys, so they form a nice commutative subalgebra of the symmetric group. They are diagonalizable on all of your simples. And if you look at the combinatorics of the weights of these guys, you would reinvent tableau. Okay. All right, so now I want to convince you that this geometric space that has the correct size, because we know it's a vector space, is a representation of the rational Cherednik algebra. All right, so in the rational Treadmic algebra, I just have to show that the symmetric group, this operator T and this other operator lambda, that they act and they satisfy the relations. So let me just sketch how they act without giving all of the details. Okay, so how should the symmetric group act? Well, you do the same thing that you do with Springer theory when you actually have flags of vector spaces. You do use these correspondences. You sort of, you know, collapse a flag and you project down and you do a push-pull. Okay, so that behaves in exactly the same way, and you do all the same proofs there. What does T do? And again, T wanted to be kind of this diagram automorphism-like thing. So my parabolic Hilbert scheme was this union over, you know, do you start at codimension K or whatnot? And I'm claiming that T is going to start with my first ideal at codimension K, and it's going to go to a flag where my first ideal has codimension K plus 1. And what it's going to basically do is I have this flag of ideals, right? The subscript is the codimension, one contained in the next, and then the last one, the nth case one, is x times it. So remember, those were like the staircase pictures. And T just takes that and it cycles it around. It says, well, start my flag at ik plus 1. Forget the information of ik. All right? And then xik is no longer the last one. I have to put some other ideal that fits inside of here. We'll just take x times ik plus 1. Well, you have to by the condition, but because ik contains ik plus 1, xik contains xik plus 1. So this is this natural kind of shifting operator. It's, you know, very natural. Okay, so it clearly gives a very nice map, and it acts on the underlying flags. So of course it acts on the homology. Whereas with the symmetric group, we didn't act on the flags, we only acted on the homology. Okay, and lambda, this other operator, it wants to go backwards from T, and it can't, because given such a flag, like, you're going to try to stick something here, like, what are you going to do? But you don't have to act on flags. You only have to act on the homology, just like with the symmetric group. And for that, you do something much more complicated, which, in the interest of time, plus my weaknesses in geometry, I'm going to just skip that. But say you can do it, you have to be a lot more delicate with the geometry, but it works. Okay, and then you can show it satisfies. So now that we know that it acts, how do we know that it's the trivial representation? I claim that the Dunkl-Opdam operators do the job for us. In other words, we know how the Dunkl-Opdam operators, we know what their weights are acting on our usual trivial representation, and we can read that off of the combinatorics of those tableaux really nicely in the sort of usual way. If you want to know the weight for like a UI, you sort of, you look in your tableau that you've made sort of periodic, and you just look for the box I, and you say, what diagonal am I on? And that is going to give you the eigenvalue. So it behaves just like if you've seen it before for symmetric group, reduces Murphy operators, or Hecke algebras, or double affine Hecke algebras. It works in just the same way. How does it work geometrically? What are my commuting operators doing geometrically, and how am I getting these flags actually being weight vectors? Okay, so I'm going to take this flag of monomial ideals specified by one of these non-negative n-tuple vectors. So one of these staircase diagrams and corresponding flag. And what UI is going to do, and I'm going to call this guy curly UI because it's not exactly our UI in the RCA. I'm going to cap at the first Chern class of the following line bundle, Li. So Li, you look at your flag, yeah, and then you look at I sub k plus I minus 1 mod I sub k plus I. So that's the same I, right? So your flag starts at some I sub k of codimension k. These guys are all relative codimension 1. So at the ith step, I've got this line bundle that marks out what's this line, this quotient. Okay. And so that's my operator UI. All right. Well, how do we compute it? So remember that we could have brought in this other parameter z and said I'm on my curve x to the m is y to the n. So we could think of x as z to the n and y as z to the m. And because of how the torus act, the equivariant weight of z is 1. And so the weight on a x to the a, y to the b is given by an plus bm, because I rewrite this in terms of z's. This is z to the an plus bm. Okay, and so let's look at our example of our flag we had before. Right, if we look at, as we go on our flag, what's the relevant monomial that we're adding or subtracting as you go from one to the other? Here, right, this was in the y squared row, and I'm at the 3. So it's x cubed y squared, which is z to the 3 times 4 plus 2 times 3, if I got them right, so it should be z to the 17. Whereas here, the next step, we put in an x to the 7th, which is z to the 21. And then the final step here, what we were adding in was x to the 5th y, which we write in terms of z as z to the 19. And so if I want to pick up how u1, u2, and u3 are acting, they care u1 cares of what's happening at this step. Sort of the new thing that's happening is the z to the 17, which has equivariant weight 17, so it's acting as 17. Likewise, u2 is acting as 21, and u3 is acting as 19. Okay. And so this describes for you, for these commuting operators, what the weights are, and that these monomial flags of monomial ideals are a weight basis, and they combinatorially describe the weights. Okay. Now, the way to connect it to the trivial representation that we know via tableau and the usual story is to kind of say, all right, these geometric operators we have to do a little bit of fiddling, changing. That has to do with the fact that geometrically we read these as 3, 7, 5, but algebraically we cared about 5, 7, 3, and that there's some like overall scaling. But let's see, I have it here. Whoops, sorry. Here we go. So, right, so we have this 1721 19 that came from 375. If we reverse it so we get 573, and so that means we take this tableau by basically taking 5 times 3 plus 1, 7 times 3 plus 2, 3 times 3 plus 3, and putting them in increasing order. The way that the UIs, the Dunkl-Opdam operators, will act, it turns out it's as 11 thirds, 13 thirds, and 9 thirds. And you can see those are not the same as 17, 21, and 19. But if you start with 17, 21, and 19, subtract 8 from everything, and you'll get 9, 13, and 11. Okay, so that's just an overall scaling. Now you read them backwards, so it becomes 11, 13, and 9. And then if you multiply by the 1/3, you'll get these numbers here. Or in other words, it's just easier, right? You see 11 thirds, 13 thirds, and 9. It's easy to read off the 11, 13, and 9. And again, that's just going to be a rescaling. And now I have to read them right to left instead of left to right. That was not a surprise because, again, the C's kind of went that way and the A's went that way. And for just some algebraic reason, there's this overall adding, subtracting of the number 8, which is m times n minus 1. And so, again, these U's are not exactly the same U's. You have to read them backwards and rescale them slightly and add an overall constant to everything. They're still going to all commute with each other. If you multiply them all by the same scalar and you also add some scalar to all of them, they're still perfectly good commuting operators. And so in this way, you line up the weights. And so you're like, aha, these two commutative subalgebras, after you massage one into the other, they act exactly the same on these two representations, on these same bases, these weight bases, like same dimension, same weights. Because all the weight spaces are one-dimensional, because you understand how this algebra works and how it fits together with this commutative subalgebra, it basically says they have no choice but to be isomorphic representations. So it's kind of a cheap proof in that it doesn't directly construct the isomorphism. It says it is a module. I know how the Dunkl-Opdam operators are acting on it, and therefore it forces it to be exactly this trivial module where I also know exactly how the Dunkl-Opdam operators act, and that's enough information to say it is this module. So yeah, that's more or less how the proof goes. I'm going to just give a little bit of a sense of what happens with this BGG resolution because we have the combinatorics built up for it. So you have a basis for your standard module. You basically have a basis that is fillings of hooks with numbers that are increasing across rows and down columns, and there's one per each conjugacy class mod n. And you basically just compare the two numbers at the ends of the hook, and you say, if you were to take A and add m plus n to it, is it greater than B or is it less than B? And if it's less than B, you sort of take A plus mn and you stick it on top here, and then you repeat the hook, adding mn everywhere else. And you keep going. Whereas if it was greater than it, you add mn to A here, and then you repeat the hook, and you keep going. But the hook here, it starts on top, and the hook here starts side by side. And doing that, you say, aha, the irreducible is indexed by these hook shapes that you make periodic in this way by stacking one hook on the next, and you still ask that it increases across rows and down columns. The kernel of this map, and that's your irreducible quotient. This submodule of things where they don't work that way and your hook would have to be taller, you say, wait a minute, I can realize this is a periodic hook where my hook is now one taller. And you say, aha, this hook that's one taller, these come from the standard of the other hook. The standard of the taller hook feeds into this map in that way, and that's giving you your resolution. So that's constructing your map from the standard of a taller hook to a shorter hook. It's exactly cutting out the image here as the fillings that you could make periodic in this way. And the kernel and the image exactly line up by whether you make them periodic by stacking the hook on top or putting the hook side by side. And when it goes on top, you can realize it is coming from a slightly taller hook, and that explains the map that came previously. So that's just a sketch of the combinatorics. I was just abusing the 2 minutes I had there, but now I'll stop.
All right, thank you for a beautiful talk. Are there any questions?
Slightly dumb, but what happens when M and N are not co-prime?
Oh yeah. So when M and N are not co-prime, so it matters, let's see. So in terms of the BGG stuff, things are more complicated. Well, okay, if M and N are not co-prime, but C is still M over N, yeah, it's way more complicated. There's some work by Eddinghoff, Gorski, and Losev that look at that a little bit.
Don't you have to tensor your, so if you had delta of mu, then you would have to tensor by exterior powers of your reflection representation to build that BGG resolution. That's how I remember it.
Okay, but you can still get the BGG resolution, but it's just.
I think so. I'm not sure.
Okay, I'm trying to remember also in terms of the, so I think also in terms of which standards are irreducible or not, it's more complicated, right? I think you can have more things that cluster into blocks together if you're in the not relatively prime case. And yeah, but I think you basically, you can compare it to the relatively prime case and you can build some things up. You can look at like, if you write M over N as like dm over dn, then, you know, you can look at the M over N case and, right, I think this is what some of what everyone was saying. You can kind of look at what's happening at the M over N case and you can, you know, bootstrap some things up here to see what's happening. But I confess, I don't have it on my fingertips. What else happens in this case?
Well, because you mentioned also like the geometry was breaking down too. And I was wondering a bit if like something was breaking down on the geometry, but not on the algebra side, but it is happening on both.
It's happening on the, so the algebra side is actually, I think, better behaved. On the geometry side, you don't have isolated fixed points.
Mm-hmm.
Yeah. For the torus action. And so what is going on with the homology and what's the basis of the homology is more complicated.
All right, thank you.
Do you have this Dunkl-Opdam subalgebra for all types?
That's a great question. I'm so type A when it comes to DAHA and RCA. I mean, you have it in the DAHA. You've got commutative subalgebra with DAHA, right? Wait, so like I feel like you should have them in other types, but I don't know how to write them down. I don't know if Dunkl-Opdam did that, and I don't know if they did it in just type A or if they did it in other types. So yeah, the original Dunkl-Opdam, I don't know if they were looking in other types. But you should, if they haven't written it, I mean, it's got to exist. I'm sure other types RCAs have a nice large commutative subalgebra such that their weight theory gives nice combinatorics that, you know, as opposed to the subalgebra that is acting nilpotently.
There's a Gelfand-Seltland subalgebra that pops out of that construction. And I think that's what these Dunkl-Opdam operators are recovering in type A. And so, for instance, Webster's work on Cherednik algebra should have, he develops like a Gelfand-Seltland representation theory for these guys pretty combinatorially. So one can look there. All right, Monica, thank you again so much.
Thanks for inviting me.